Hey everyone, it's Micah here with a quick walkthrough tutorial on question 4, range query of worksheet 11, midterm review practice. The question asks to write a function that counts the number of elements greater than a given number in a binary search tree. Assume the binary search tree node has methods label, left, and right. So recall that a binary search tree has three main rules. The first rule is here. Every node has a max of 2 children, left and right. It can have 1 child, it could have 0 children, 2 children, but no more than that. The second and third rule relate to each other in that all left nodes are less than the root and all right nodes are greater than the root. So if that wasn't clear enough, here is a visual example for you. You see here 8 is the root at the top of the tree, and then to the left is a 3, which is, as we see, less than 8, and this 10 is greater than 8. And you see that that pattern continues for every node in every other level. So for the 6 here, the 4 is less than 6, the 7 is greater than 6, and so on and so forth. You should be pretty familiar with binary search trees by now. So let's go over the solution to this problem together. So find greater takes in a tree t and a binary search tree t and an integer x. I always start with the base case, okay? This is the skeleton code that we're given. So I don't know right off the bat what the base case is, but what's most common in tree problems, especially ones that use recursion, is that we are asked to check if t is null. Okay, and this is usually the case. Another quick aside is that for tree problems, it's really great practice to use recursion. You should always try to use recursion for binary tree problems. The solution is cleaner that way. We'll see later in the class that recursion isn't always the approach for tree problems, but for trees where there are a fixed number of children, it's great to use recursion. Okay, so I always like to start with an example when understanding this problem. So I'm going to pretend that T is this tree here, and that we want to find all elements greater than 9, or greater than 8 even. So starting with the base case, as we said before, we're going to check if T is null. And if T is null, what do we return? So recall that we are counting the number of elements greater than the given number of binary search trees. So if T is null, how many elements are greater than 8, for example? 0. So there are 0 elements greater than whatever the input x is, in this case 8. So because that's the case, we would return 0. Now let's move on to the recursive case. So there are two things that can really happen here. It's great to look at the example again. Recall that we want to count the number of elements greater than x. So when I recurse down my tree and hit new nodes, there are two cases. Either the node is larger than x, or the node is not larger than x. And since we're counting the number of elements greater than x, let's consider what to do for each of the cases. And really the case is, as I mentioned, we're checking if the node is greater than x, specifically if node.label is greater than x. So if node.label is greater than x, what do we return? Well, we're counting, so we're going to add 1 to whatever our return statement is, our recursive return statement is. So now we want to check the rest of the nodes. So I have a node, like let's say I'm at 10. 10 is greater than 1, is greater than 8. So I'm going to add 1 to whatever I return and then check the rest of the nodes under 10. So to do that, I return this t.left and t.right. Okay. Now, what about this case? Well, in this case, the label, t.label, the node, is not greater than x, so you could think, oh, we would return 0 plus a recursive call. So we could technically just check the left and right again, like this, and technically the solution would be correct. But we can do a little bit better here. So recall that for a binary search tree, all left nodes are less than the root, okay? So for this example, all nodes to the left of 8, say we're at the node 8, all nodes to the left of 8 will be less than it. So since we know that 8 is less than our input x, which was 9, we know that we can't do any better if we check all the nodes to the left of 8. And we can see empirically here that all these nodes are also less than 9, so won't be included in the check anyways. So it would be better or more efficient if we just checked the right of the tree. And we're done.